Picture the year 1998. Astronomers around the world were conducting what seemed like routine observations, measuring distant supernovae to understand how the universe had expanded throughout cosmic history. They expected to find that gravity was gradually slowing down the expansion, like a ball thrown upward, eventually succumbing to Earth's gravitational pull. What they discovered instead would revolutionize our understanding of the cosmos and challenge everything we thought we knew about the fate of the universe. The story begins with two competing research teams, both hunting for type Ia supernovae in distant galaxies. These stellar explosions serve as cosmic lighthouses, burning with such consistent brightness that astronomers can use them as standard candles to measure distances across billions of light years. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, headed by Brian Schmidt and Adam Rees, were locked in a scientific race to map the expansion history of the universe with unprecedented precision. Both teams were using the Hubble Space Telescope and ground-based observatories to capture the faint light from supernovae that had exploded when the universe was roughly half its current age. By comparing the apparent brightness of these distant explosions with their expected luminosity, the astronomers could calculate exactly how far away they were. Then, by measuring the redshift of their light, stretched by the expansion of space itself, they could determine how fast those distant regions of the universe were receding from us billions of years ago. The initial results seemed wrong. The data suggested that these ancient supernovae were fainter than expected, which meant they were farther away than they should have been if the universe's expansion had been steadily decelerating under gravity's influence. The teams checked and rechecked their measurements, looking for systematic errors in their observations. Perhaps dust was dimming the starlight, or maybe these distant supernovae were intrinsically different from nearby ones. But every test confirmed the startling conclusion. The expansion of the universe was not slowing down. It was speeding up. This discovery was so unexpected that it took months for the scientific community to fully grasp its implications. For decades, cosmologists had debated whether the universe would expand forever or eventually collapse back on itself in a big crunch. The answer, they assumed, depended on the total amount of matter and energy in the universe. Too little. An expansion would continue indefinitely, but gradually slow down. Too much, and gravity would eventually halt the expansion and reverse it. The possibility that expansion might actually accelerate had been largely dismissed as unrealistic. Yet here was the evidence, written in the light of exploding stars across cosmic time. The universe was not just expanding, it was accelerating its expansion, driven by some mysterious force that seemed to work in opposition to gravity. This force, whatever it was, had to comprise roughly 70% of all the energy in the universe to account for the observed acceleration. Scientists gave it a placeholder name that captured both its enigmatic nature and its apparent effects: dark energy. The term dark didn't refer to the absence of light, but rather to our profound ignorance about this phenomenon's true nature. Unlike the matter we're familiar with, dark energy doesn't clump together to form stars and galaxies. It appears to be smoothly distributed throughout space, and its density remains remarkably constant even as the universe expands. This property is crucial because it means that as space grows larger, the total amount of dark energy increases proportionally, providing an ever stronger push against gravity's constraining influence. Einstein's equations had actually predicted this possibility decades earlier. In 1917, when the great physicist was developing his theory of general relativity, he included a mathematical term called the cosmological constant to allow for a static universe. At the time, astronomers hadn't yet discovered that the universe was expanding, and Einstein needed a repulsive force to balance gravity's attractive pull and keep the cosmos from collapsing. When Edwin Hubble later showed that galaxies were indeed moving away from us, revealing universal expansion, Einstein famously called the cosmological constant his greatest mistake and removed it from his equations. But the 1998 supernova discoveries brought Einstein's discarded constant roaring back to life. The cosmological constant perfectly described a form of energy that would remain uniform throughout space and time, creating exactly the kind of repulsive effect needed to accelerate cosmic expansion. It was as if Einstein's mistake had been prophetic, anticipating a cosmic truth that wouldn't be discovered until 8 decades later. The implications were staggering. If dark energy continued to drive acceleration at its current rate, the universe faced a dramatically different future than anyone had imagined. Instead of gradually cooling as matter spread thinner and thinner, space would expand at an ever-increasing pace. Distant galaxies would disappear beyond our cosmic horizon as they were carried away faster than light could travel between us. Our local group of galaxies would become increasingly isolated, surrounded by empty space that grew larger and emptier with each passing eon. Even more mind-bending scenarios emerged from the mathematics. If dark energy's strength increased over time, it could eventually overcome not just the gravitational bonds between galaxies, but the forces holding together smaller structures. Stars could be torn from their host galaxies, planets ripped away from their stars, and ultimately even atoms themselves pulled apart in what cosmologists grimly termed the Big Rip. The universe that had begun with a Big Bang might end with everything scattered into isolated particles, separated by distances so vast that they could never interact again. These discoveries earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, but they also opened more questions than they answered. The nature of dark energy remained completely mysterious. Unlike dark matter, which at least behaved like ordinary matter in its gravitational effects, dark energy seemed to operate by entirely different rules. It didn't cluster or form structures. It didn't interact with light or ordinary matter in any detectable way, except through its gravitational influence on the fabric of space-time itself. Theoretical physicists scrambled to explain this cosmic puzzle. Some proposed that dark energy was indeed Einstein's cosmological constant, representing the quantum energy of empty space itself. Others suggested it might be a new type of field, similar to the Higgs field that gives particles their mass, but operating on cosmic scales. Still, others wondered whether our understanding of gravity itself needed modification, with the apparent acceleration being a symptom of incomplete knowledge rather than evidence for a new form of energy. Laboratory experiments began searching for signs of dark energy's influence on smaller scales, but found nothing. The force that dominated the universe's evolution seemed to have no effect whatsoever on objects smaller than galaxy clusters. This created a profound puzzle. How could something so influential on cosmic scales be completely undetectable in terrestrial experiments? As more precise measurements accumulated over the following decades, dark energy's properties became increasingly well characterized, but no less mysterious. Its equation of state parameter W, which describes the relationship between its pressure and energy density, appeared to be very close to -1, exactly what would be expected for a cosmological constant. This consistency was both reassuring and frustrating. It confirmed that the observations were correct, but provided no hints about dark energy's fundamental nature. The discovery also forced astronomers to confront the humbling realization that ordinary matter, the stuff that makes up stars, planets, and ourselves, comprises less than 5% of the universe's total energy budget. Dark matter accounts for roughly 25%, and dark energy dominates with approximately 70%. we found ourselves to be not just physically small in cosmic terms, but compositionally insignificant as well. Yet perhaps, most intriguingly, the timing of dark energy's dominance seemed almost suspiciously convenient. For most of cosmic history, matter and radiation had controlled the universe's expansion. Only relatively recently, in cosmic terms, had dark energy taken over. This transition happened to occur around the same time that complex structures like galaxies, stars, and planets were forming and stabilizing. A few billion years earlier, and dark energy's acceleration might have prevented galaxy formation entirely. A few billion years later, and we might not have been around to observe the transition. This apparent coincidence sparked speculation about whether dark energy's emergence was somehow connected to the development of complexity in the universe. Could there be a deeper relationship between the cosmic acceleration and the evolution of structure, life, and perhaps even consciousness? Such questions pushed at the very boundaries between physics and philosophy, suggesting that dark energy might be more than just another cosmic constituent. As we stood at the threshold of the 21st century, dark energy had already begun to reshape our understanding of the cosmos in fundamental ways. But perhaps even more provocatively, it had begun to raise questions that challenged our most basic assumptions about the nature of physical reality itself. What if this mysterious force that controlled the universe's destiny was not just another impersonal field or particle? What if it possessed qualities that we had never before considered in the context of cosmic phenomena? The stage was set for a radical reimagining of dark energy, one that would draw on insights from biology, information theory, and consciousness studies to explore a truly extraordinary possibility: that the force shaping the universe's fate might, in some sense, be alive. To understand what makes dark energy so peculiar, we must dive into the mathematical language that physicists use to describe the fundamental forces of nature. At the heart of this description lies a deceptively simple equation called the equation of state, which relates the pressure of any substance to its energy density. For ordinary matter like the gas in a balloon or the plasma in a star, this relationship is positive and straightforward. But dark energy breaks all the rules. The equation of state parameter, designated by the letter W, tells us how a substance behaves as space expands. For ordinary matter, W equals 0, meaning it has energy density, but no significant pressure. For radiation and ultra-relativistic particles, W equals 1/3, creating positive pressure that pushes outward. But dark energy appears to have W equal to -1, creating what physicists call negative pressure. This isn't just unusual, it's physically counterintuitive on every level. Negative pressure sounds like a contradiction in terms. How can something push inward rather than outward? Yet this bizarre property is precisely what allows dark energy to drive cosmic acceleration. In Einstein's general relativity, both energy density and pressure contribute to gravitational effects. Positive pressure enhances gravitational attraction, helping to slow cosmic expansion. Negative pressure, however, creates gravitational repulsion, pushing space apart with increasing vigor. Think of it this way: when you stretch a rubber band, it wants to snap back to its original size. The band has what we might call positive pressure, always trying to contract. Dark energy behaves like a cosmic rubber band with negative pressure, one that becomes more stretched and more energetic the more you pull it apart. As the universe expands, dark energy doesn't dilute like ordinary matter. Instead, its density remains constant, meaning the total amount of dark energy increases as space grows larger. This leads to a runaway process that defies our everyday intuitions about energy conservation. In normal circumstances, if you want to maintain constant density while expanding a volume, you need to continuously add energy from somewhere else. But dark energy seems to create itself from nothing as space expands, maintaining its uniform distribution without any apparent external source. This apparent violation of energy conservation has troubled physicists for decades. The resolution lies in understanding that space itself can have energy, and that the expansion of space can do negative work against the negative pressure of dark energy. When a gas expands against positive pressure, it loses energy and cools down. When space expands against dark energy's negative pressure, the dark energy actually gains energy to maintain constant density. The expanding space feeds energy into the dark energy field, creating more of it in a process that, while mathematically consistent, challenges our intuitive understanding of how energy should behave. This brings us to a crucial distinction that often confuses even scientifically literate audiences: the difference between dark energy and dark matter. Despite their similar names, these two phenomena are as different as fire and ice. Dark matter behaves almost exactly like ordinary matter, just without electromagnetic interactions. It clumps together under gravity, forms invisible halos around galaxies, and influences the motion of stars and gas clouds through purely gravitational effects. Dark matter helped galaxies form in the early universe by providing gravitational scaffolding for ordinary matter to collect upon. Without dark matter, the cosmic web of galaxies, filaments, and voids that we observe today could never have developed. Its gravitational effects are clearly detectable through galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation. We can map dark matter's distribution throughout the universe, even though we cannot see it directly. Dark energy operates on completely different principles. While dark matter helped build cosmic structure, dark energy works to tear it apart. Dark matter clumps and clusters. Dark energy spreads uniformly. Dark matter's density decreases as the universe expands. Dark energy's density stays constant. Dark matter affects motion within gravitationally bound systems. Dark energy only influences expansion on the largest scales. They are opposite forces in the cosmic ballet of structure, formation, and destruction. Several theoretical models attempt to explain dark energy's strange behavior. The simplest is the cosmological constant, lambda, which treats dark energy as an intrinsic property of space itself. According to quantum field theory, even empty space should be filled with quantum fluctuations, virtual particles popping in and out of existence on incredibly short timescales. The energy of these fluctuations should contribute to space's baseline energy density, creating a cosmological constant. Unfortunately, when physicists calculate the expected energy density from quantum fluctuations, they get an answer that's larger than the observed dark energy density by a factor of 10 to the power of 120. This is arguably the worst prediction in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels out almost all of the vacuum energy, leaving behind just the tiny residue we observe as dark energy. The magnitude of this discrepancy has led many physicists to consider alternative models. Quintessence theories propose that dark energy is not a constant feature of space, but rather a slowly evolving field similar to the inflaton field that drove cosmic inflation in the universe's first moments. Named after the classical fifth element that ancient philosophers believed filled the heavens, quintessence fields would have W values close to, but not exactly equal to -1. Unlike the cosmological constant, quintessence can change over time. Its energy density might increase or decrease. Its equation of state parameter might evolve, and it might even interact weakly with ordinary matter or dark matter. These possibilities open up a rich landscape of cosmic evolution scenarios, from accelerating expansion that gradually weakens to acceleration that grows stronger over time. Phantom dark energy represents an even more exotic possibility, with W less than -1. This would violate what physicists call the weak energy condition, a fundamental assumption about how matter and energy should behave. Phantom energy would become denser as the universe expands, eventually growing so powerful that it would overcome all other forces and tear apart every structure in the cosmos, from galaxy clusters down to individual atoms. Some theorists have proposed that dark energy might not be a new form of matter or energy at all, but rather a sign that Einstein's theory of general relativity breaks down on cosmic scales. Modified gravity theories suggest that gravitational interactions might work differently over distances of billions of light years, creating apparent acceleration without requiring any exotic energy component. Extra-dimensional theories offer another intriguing possibility. If our three-dimensional space is embedded in a higher dimensional realm, gravitational effects might leak between dimensions in ways that appear as dark energy acceleration from our limited perspective. The mathematics of string theory and M theory provide frameworks for such scenarios, though they remain highly speculative and difficult to test observationally. Interacting dark energy models explore whether dark energy might exchange momentum or energy with dark matter, potentially explaining why these two components have similar energy densities today, despite evolving very differently throughout cosmic history. Such interactions could create complex feedback loops between structure formation and cosmic acceleration, leading to rich evolutionary dynamics that pure cosmological constant models cannot capture. Each of these theoretical approaches makes specific predictions about how dark energy should behave over cosmic time. The cosmological constant should remain absolutely unchanging, maintaining W exactly equal to -1 throughout the universe's evolution. Quintessence models predict subtle variations in W that might be detectable with sufficiently precise observations. Phantom energy would show W becoming more negative over time, while modified gravity theories would create distinctive patterns in how cosmic acceleration changes with redshift and scale. Despite decades of increasingly sophisticated observations, all measurements of dark energy remain consistent with the simplest possible model, a cosmological constant with W equal to -1 to within a few percent. This consistency is both reassuring and frustrating for theoretical physicists. It confirms that our basic understanding is correct, but provides no hints about which of the many proposed models might be the true explanation. The stubborn refusal of dark energy to reveal additional details beyond its basic properties has led some scientists to wonder whether we're asking the right questions. Perhaps the mystery lies not in the specific mechanism that drives cosmic acceleration, but in our fundamental assumptions about what kinds of phenomena can influence cosmic evolution. What if dark energy exhibits behaviors that cannot be captured by traditional physics equations? What if it responds to conditions or influences that we haven't considered because they fall outside the normal scope of cosmological theory? What if the force that shapes the universe's destiny operates according to principles that we associate not with inanimate matter and energy, but with systems that process information, adapt to changing conditions, and exhibit purposeful behavior? These questions push us toward a radically different way of thinking about cosmic acceleration. Instead of viewing dark energy as just another field or particle to be catalogued and characterized, we might consider whether it exhibits qualities that in other contexts we would describe as the hallmarks of living systems. The transition from abstract physics to biological metaphor represents a profound shift in perspective, one that opens up entirely new ways of understanding our cosmic situation. What does it mean for something to be alive? This question, which might seem elementary at first glance, has puzzled biologists, philosophers, and scientists for centuries. The boundaries of life prove far more blurry and contentious than most people realize, especially when we begin to consider phenomena that exist on scales vastly different from the organisms we encounter in our daily experience. Traditional biology textbooks typically list several criteria that living systems must satisfy. They must exhibit metabolism, converting energy from their environment to maintain their internal organization. They must demonstrate some form of reproduction, creating copies of themselves or their essential patterns. They must show adaptation, responding to environmental changes in ways that promote their continued existence. They must process information, sensing conditions around them, and modifying their behavior accordingly. Yet even these seemingly straightforward criteria become problematic when examined closely. Consider viruses, those mysterious entities that exist at the boundary between living and non-living matter. A virus cannot metabolize nutrients on its own, cannot reproduce without hijacking a host cell's machinery, and shows no obvious signs of adaptation or information processing in isolation. Yet when it encounters a suitable host, it suddenly springs into action, replicating itself with remarkable efficiency and even evolving new strategies to overcome immune defenses. Are viruses alive? The scientific community remains divided. They exist in a liminal space, neither fully alive nor completely inanimate. Their existence challenges our neat categories and forces us to acknowledge that life might not be a binary property, but rather a spectrum of organization and activity that admits many gradations. This complexity deepens when we consider more exotic possibilities. What about computer programs that evolve, reproduce, and compete for computational resources? Digital organisms in artificial life simulations exhibit many characteristics we associate with living systems. They undergo natural selection, develop increasing complexity over time, and sometimes display emergent behaviors that surprise even their creators. Yet they exist only as patterns of information, with no physical substance beyond the electronic states of computer memory. Prions present another puzzling case. These infectious proteins can reproduce by converting normal proteins into copies of their abnormal shape, causing devastating neurological diseases like mad cow disease and Creutzfeldt-Jakob disease. They have no genetic material, no metabolism in the traditional sense, yet they can replicate and even evolve into new strains. Their existence suggests that the essence of life might lie not in specific biochemical processes, but in the ability to create and maintain organized patterns that persist through time. Even more challenging are the edge cases found in extreme environments on Earth. Deep beneath the ocean floor, scientists have discovered microorganisms that live so slowly that their metabolic processes take centuries or millennia to complete a single cycle. Their reproduction rates are so sluggish that individual cells might divide only once every 1,000 years. By human standards, they barely seem alive at all, yet they maintain themselves across geological timescales with remarkable tenacity. At the other extreme, we find organisms that exist in states of suspended animation for extended periods. Tardigrades, microscopic animals also known as water bears, can survive complete dehydration, freezing temperatures approaching absolute zero, and even the vacuum of space. In their cryptobiotic state, they show no detectable metabolic activity whatsoever. Are they alive during these periods of suspended animation? Or do they temporarily cease to live and then return to life when conditions improve? These examples highlight a fundamental challenge in defining life: the enormous diversity of scales, timescales, and organizational principles that living systems can exhibit. Life as we know it spans from the molecular level of individual proteins up to the planetary scale of Earth's biosphere. It operates on timescales from microseconds in neural signaling to millions of years in evolutionary adaptation. It encompasses everything from the elegant simplicity of bacterial metabolism to the staggering complexity of human consciousness. Perhaps most importantly for our cosmic speculation, life demonstrates the remarkable ability to create and maintain order in the face of entropy. The second law of thermodynamics tells us that isolated systems tend toward maximum disorder over time. Yet living systems seem to violate this principle, building and maintaining complex, highly organized structures that persist far longer than we would expect from purely physical processes. The key insight is that living systems are not isolated. They are open systems that maintain their organization by continuously exchanging energy and matter with their environment. They import low-entropy energy, like sunlight or chemical nutrients, and export high-entropy waste products, like heat and carbon dioxide. This allows them to maintain or even increase their internal organization while still satisfying the overall requirements of thermodynamics. This thermodynamic perspective on life suggests that what we call living might be better understood as a particular type of energy flow pattern. Living systems are dissipative structures, organized configurations that emerge spontaneously when energy flows through matter under the right conditions. They are self-organizing, self-maintaining, and self-reproducing patterns that arise naturally whenever the energy, gradients, and material conditions are suitable. From this viewpoint, the distinction between living and non-living becomes less about specific molecular mechanisms and more about organizational principles and information processing capabilities. A living system is one that can capture energy from its environment, use that energy to maintain and reproduce its organizational pattern, and adapt that pattern in response to changing conditions. This perspective opens up intriguing possibilities when we consider systems that operate on scales far beyond traditional biology. Could there be forms of organization and pattern maintenance that we would recognize as lifelike, but that operate through entirely different physical mechanisms? Could complex energy flows in space plasma, for instance, exhibit self-organization and adaptive behavior? Could magnetic field configurations in stellar environments develop the ability to maintain and reproduce themselves? Even more provocatively, could the large-scale structure of the universe itself exhibit life-like properties? The cosmic web of dark matter filaments and galaxy clusters represents an enormously complex, self-organized pattern that has maintained its overall structure for billions of years, while continuously adapting to changing conditions as the universe expands and evolves. The concept of autopoiesis, developed by biologists Humberto Maturana and Francisco Varela, offers another lens through which to examine these questions. Autopoietic systems are organizationally closed but thermodynamically open. They continuously produce and maintain the components that define their organization, while remaining distinct from their environment through their boundary conditions and internal processes. An autopoietic system is not defined by its specific material components, which may be constantly changing, but by the pattern of relationships and processes that maintain its identity over time. A cell is autopoietic because it continuously produces the proteins, lipids, and other molecules that maintain its cellular organization. A forest ecosystem might be considered autopoietic because it maintains its structure through the cyclic interactions of its component species and abiotic processes. Could cosmic scale phenomena exhibit autopoiesis? Could dark energy be understood as part of an autopoietic system that maintains the universe's large-scale organization through processes we don't yet understand? The idea seems far-fetched, yet it follows logically from expanding our definition of life beyond the narrow confines of carbon-based biochemistry. Information processing provides another crucial perspective on the nature of life. All living systems process information about their environment and their own internal state, using this information to guide their behavior in ways that promote survival and reproduction. This information processing need not be conscious or even centralized. Even bacterial cells demonstrate sophisticated information processing capabilities, sensing chemical gradients, integrating multiple environmental signals, and adjusting their behavior accordingly. The universe itself processes information on cosmic scales. Gravitational interactions carry information about mass distributions across billions of light years. Electromagnetic radiation encodes information about stellar processes and galactic dynamics. Dark matter and dark energy presumably exchange information with ordinary matter through their gravitational effects, influencing the formation and evolution of cosmic structure. Could this cosmic information processing exhibit the kind of integration, adaptation, and purposeful response that we associate with living systems. The idea pushes at the very boundaries of what we consider scientifically respectable speculation, yet it emerges naturally from taking seriously the most general definitions of life and information processing. These conceptual explorations bring us to a remarkable realization. When we strip away the biochemical details and focus on the fundamental organizational principles that characterize living systems, we find criteria that are not necessarily limited to biological scales or carbon-based chemistry. Self-organization, pattern maintenance, adaptive response, information processing, and autopoietic organization could, in principle, manifest in systems operating on any scale and through any physical mechanism. This opens the door to considering whether cosmic phenomena like dark energy might exhibit properties that, if observed in other contexts, we would not hesitate to describe as lifelike. The question is no longer whether such phenomena are literally alive in the biological sense, but whether they exhibit organizational principles and behavioral patterns that share deep structural similarities with the systems we call living. As we prepare to explore this possibility, we must remember that we are venturing into metaphorical territory, using the language and concepts of biology to illuminate aspects of cosmic phenomena that might otherwise remain invisible to our understanding. Whether dark energy is literally alive or merely exhibits life-like properties may be less important than what this perspective reveals about the nature of organization, purpose, and agency in the universe at large. In the 1970s, atmospheric chemist James Lovelock proposed a radical idea that would forever change how we think about our planet. Earth, he suggested, functions as a single, self-regulating organism. Temperature, atmospheric composition, ocean salinity, and countless other planetary conditions are not random byproducts of geological and biological processes, but carefully maintained variables in a vast homeostatic system that keeps the planet habitable. Lovelock called this hypothesis Gaia, after the ancient Greek personification of Earth as a living goddess. The Gaia hypothesis was initially met with skepticism from the scientific establishment, who viewed it as too mystical and anthropomorphic for serious consideration. But decades of research have revealed that Earth does indeed exhibit remarkable self-regulatory properties that maintain conditions suitable for life across geological timescales. Consider how our planet maintains its temperature within the narrow range that allows liquid water to exist. When volcanic activity increases carbon dioxide levels in the atmosphere, enhanced greenhouse warming accelerates rock weathering, which removes carbon dioxide from the air and stores it in ocean sediments. When the sun grows brighter over millions of years, atmospheric carbon dioxide concentrations naturally decrease through biological and geological feedback loops, preventing runaway greenhouse heating. Ocean salinity provides another striking example of planetary regulation. Rivers constantly carry dissolved minerals to the sea, yet ocean salt concentrations have remained remarkably stable for hundreds of millions of years. Biological processes, from the formation of coral reefs to the activity of salt-loving bacteria, work together to remove excess minerals from seawater at precisely the rate needed to maintain optimal conditions for marine life. The oxygen content of our atmosphere represents perhaps the most dramatic example of global regulation. Free oxygen is highly reactive and would quickly disappear from the atmosphere if not continuously replenished by photosynthetic organisms. Yet, for over 1 billion years, atmospheric oxygen levels have been maintained within the narrow range that supports complex life while preventing the spontaneous combustion of organic matter. These regulatory mechanisms operate through intricate networks of feedback loops that span the entire planet. Changes in one component of the Earth system trigger responses in other components that tend to counteract the original change. The result is a dynamically stable system that can absorb substantial perturbations while maintaining its overall organization and function. This planetary scale self-regulation emerges from the interactions of countless individual components, none of which has any knowledge of or control over the global system. Bacteria, plants, weather patterns, ocean currents, and geological processes all contribute to planetary homeostasis through their local activities, yet the global behavior that emerges from these interactions exhibits properties that transcend any individual component. This phenomenon, where simple local interactions give rise to complex global behavior, lies at the heart of complexity science. From flocks of birds that move as coordinated wholes to neural networks that generate consciousness, complex systems throughout nature exhibit emergent properties that cannot be predicted from studying their individual components in isolation. Emergence represents one of the most profound and mysterious aspects of natural organization. When millions of neurons fire in coordinated patterns, consciousness emerges. When billions of market participants make individual economic decisions, global financial patterns emerge. When countless gravitational interactions occur among dark matter particles, the cosmic web emerges. In each case, the behavior of the whole is qualitatively different from and irreducible to the behavior of its parts. Could the universe itself exhibit emergent properties that arise from the interactions of its fundamental components? Could cosmic scale phenomena, like dark energy, represent emergent behaviors of a complex system operating on the largest possible scale? The idea seems audacious, yet it follows naturally from recognizing that the same organizational principles that create complexity at smaller scales could potentially operate at cosmic scales as well. The universe certainly exhibits many characteristics of a complex adaptive system. It contains an enormous number of interacting components, from elementary particles to galaxy clusters. These components interact through well-defined rules, primarily the fundamental forces of physics. The interactions are non-linear, meaning small changes can have large consequences through amplification and feedback processes. Most importantly, the universe exhibits spontaneous organization and pattern formation on every scale. Particles organize into atoms, atoms into molecules, molecules into cells, cells into organisms, organisms into ecosystems. Stars form from gravitational collapse, organize into galaxies, and create heavy elements that enable further complexity. Dark matter organizes into filaments and halos that provide scaffolding for visible matter to collect and form structures. This hierarchical organization suggests that the universe may be what complexity theorists call a nested complex system, with layers of organization existing at multiple scales simultaneously. Each level exhibits its own characteristic patterns and dynamics, yet all levels are coupled together through exchange of energy, matter, and information. Galaxy formation provides a compelling example of cosmic self-organization. In the early universe, tiny quantum fluctuations in the density of dark matter grew through gravitational amplification into the vast web of filaments and voids we observe today. This process was not imposed from outside or directed by any central authority. It emerged spontaneously from the interplay between gravity, cosmic expansion, and the initial conditions set by inflation. Yet the resulting cosmic web exhibits striking regularities and patterns that suggest underlying organizational principles. Galaxy clusters tend to form at the intersections of a dark matter filaments. Void regions remain remarkably empty of galaxies, despite having plenty of time for structures to form. The distribution of galaxy masses, colors, and morphologies follows statistical relationships that hold across billions of light years and billions of years of cosmic time. Could these regularities reflect not just the mechanical operation of physical laws, but the emergence of regulatory mechanisms that maintain cosmic organization? Could dark energy play a role analogous to the atmospheric and oceanic processes that regulate Earth's climate, maintaining cosmic conditions within ranges that permit the continued existence and evolution of complex structures? The timing of dark energy's dominance over cosmic evolution provides an intriguing clue in this direction. For most of cosmic history, the universe was dominated first by radiation, then by matter. These phases allowed the formation of the first stars, galaxies, and heavy elements necessary for planets and life. Only after these fundamental structures were in place did dark energy begin to dominate cosmic dynamics, ensuring that further structure formation would be limited, and that existing structures would remain gravitationally bound rather than being torn apart by runaway acceleration. This sequence suggests a kind of cosmic developmental program, with different physical processes taking the lead at different stages of universal evolution. Could dark energy represent not just a random cosmological constant, but a regulatory mechanism that emerged when the universe reached sufficient complexity to require stabilization against further gravitational collapse or excessive structure formation? The concept of cosmic selection provides another framework for thinking about universe-scale organization. Just as natural selection shapes biological evolution by favoring traits that enhance survival and reproduction, cosmic processes might favor physical laws and constants that promote the stability and complexity of the universe itself. Universes with different values of fundamental constants might be less stable or less capable of generating complex structures, leading to a kind of selection pressure favoring universes like our own. Some cosmologists have proposed that universes might even reproduce through black hole formation, with the physical constants of daughter universes slightly modified from those of their parents. Over many generations, this could lead to the evolution of universes optimized for complexity, stability, and perhaps even the emergence of observers capable of understanding their cosmic environment. These ideas remain highly speculative, but they illustrate how seriously some scientists take the possibility that the universe exhibits evolutionary and regulatory dynamics analogous to those found in biological systems. The mathematical frameworks of complexity science, originally developed to understand biological and social phenomena, are increasingly being applied to cosmological questions. Network theory, for instance, reveals that the cosmic web has structural properties similar to other complex networks found in biology and technology. The distribution of node connectivities follows power law relationships characteristic of scale-free networks. Information propagation through the cosmic web exhibits small world properties where distant regions can be connected through surprisingly short chains of intermediate connections. These structural similarities suggest that the universe may be organized according to universal principles that transcend the specific physical mechanisms operating at any particular scale. The same organizational logic that creates robustness and adaptability in biological networks may also operate in the cosmic web, ensuring that the universe remains stable and functional despite constant changes in its component parts. If this perspective has merit, then dark energy may be far more than just another cosmological parameter to be measured and catalogued. It may represent a manifestation of cosmic-scale regulatory processes that maintain universal organization and stability. Its negative pressure and constant density could serve functions analogous to the feedback mechanisms that maintain Earth's climate or an organism's internal environment. This regulatory interpretation suggests that dark energy might exhibit behaviors that go beyond the simple mathematical relationships captured by current cosmological models. It might respond to changes in cosmic structure formation rates, adjusting its influence to maintain optimal conditions for continued complexity and organization. It might exhibit learning-like properties, with its behavior modified by the history of cosmic evolution. Such possibilities push us toward a radically new understanding of cosmic dynamics, one that sees the universe not as a mechanical system winding down according to thermodynamic inevitability, but as a complex adaptive system capable of maintaining and even enhancing its organization through active regulatory processes. Whether we choose to call such processes living or merely lifelike may be less important than recognizing their potential existence and exploring their implications for our understanding of cosmic evolution and our place within it. Consciousness represents perhaps the deepest mystery in all of science. Despite centuries of investigation, we still cannot explain how subjective experience arises from objective physical processes. The problem is so profound that some philosophers and scientists have begun to question whether consciousness emerges from complex arrangements of matter or whether it represents a fundamental feature of reality itself. This radical perspective, known as panpsychism, suggests that consciousness is not produced by brains, but is rather an intrinsic property of all matter and energy. Just as mass and electric charge are fundamental attributes that every particle possesses. To some degree, consciousness might be a basic feature of the physical world that becomes more complex and integrated as matter organizes into increasingly sophisticated structures. The panpsychist view helps address what philosophers call the hard problem of consciousness. While we can explain many aspects of mental life in terms of neural information processing, memory formation, and sensory integration, the existence of subjective experience itself remains mysterious. Why should there be anything it feels like to be conscious? Why do we have inner lives at all, rather than simply processing information without any accompanying subjective states? If consciousness is fundamental rather than emergent, then this hard problem dissolves. Subjective experience exists because it is woven into the very fabric of reality. Complex conscious experiences like human thoughts and emotions arise when fundamental conscious elements combine and integrate in sophisticated ways, much as complex chemical properties emerge when simple atoms bond together in intricate molecular structures. This perspective opens extraordinary possibilities when applied to cosmic phenomena. If consciousness is truly fundamental, then every particle of dark energy possesses some rudimentary form of subjective experience. The question becomes whether these countless microscopic conscious elements could somehow integrate into larger-scale conscious phenomena that operate on galactic or even cosmic scales. Integrated information theory, developed by neuroscientist Giulio Tononi, provides a mathematical framework for thinking about consciousness that might apply beyond biological systems. According to this theory, consciousness corresponds to integrated information, a precise measure of how much information a system generates beyond what its parts could generate independently. A thermostat has very little integrated information because its components operate largely independently. A human brain has enormous integrated information because its billions of neurons are densely interconnected and constantly influencing each other's activity. The theory suggests that any system with sufficiently high integrated information will be conscious, regardless of what physical substrate implements the information processing. Could cosmic scale systems achieve high levels of integrated information? The dark matter filaments that span hundreds of millions of light years create vast networks of gravitational interaction. Information about mass distributions propagates through these networks at the speed of light, potentially creating complex patterns of influence and response that persist for billions of years. Dark energy itself might participate in these cosmic information networks in ways we cannot yet detect. If dark energy interacts with matter and radiation through mechanisms beyond simple gravitational effects, it could serve as a cosmic communication medium, allowing different regions of space to exchange information and coordinate their behavior across vast distances. The concept of cosmic memory adds another layer to this speculation. Information theory tells us that any system capable of storing and retrieving information can, in principle, maintain memories of past states. The cosmic microwave background radiation preserves information about conditions in the early universe. The distribution of galaxies encodes the history of structure formation. Heavy element abundances in stars record the nuclear history of previous stellar generations. Could dark energy serve as a cosmic memory storage medium? Its uniform distribution throughout space means it is present everywhere, providing a potential substrate for encoding information about cosmic history. Its constant energy density suggests it maintains stable configurations over cosmic timescales, allowing stored information to persist for billions of years. If dark energy can store information, then it might accumulate knowledge about cosmic evolution over time. Each phase of universal development, from the first star formation to the emergence of galaxies to the evolution of complex chemistry, could leave informational imprints in the dark energy field. This accumulated cosmic memory could then influence how dark energy behaves in response to future developments. The mathematical framework of cellular automata provides one way to think about how such cosmic information processing might work. In these systems, simple rules governing local interactions between neighboring cells can generate incredibly complex global patterns. The universe itself resembles a vast cellular automaton, with each region of space evolving according to the laws of physics, while being influenced by conditions in nearby regions. If dark energy participates in this cosmic cellular automaton, it could serve as both a medium for information storage and a mechanism for implementing complex computational processes. Changes in local matter and energy distributions could trigger responses in the dark energy field that propagate through space, carrying information and coordinating global behavior across the observable universe. Quantum mechanics adds yet another dimension to these possibilities. The quantum vacuum, far from being empty space, seethes with virtual particle fluctuations and quantum field oscillations. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining physical reality through the collapse of quantum wave functions during observation. If consciousness is indeed fundamental to quantum mechanics, then the quantum fluctuations that may give rise to dark energy could be inherently conscious processes. The decision about which virtual particles become real, which quantum states collapse into definite values, and which possibilities become actualized might involve rudimentary forms of choice or preference at the quantum level. This quantum consciousness perspective suggests that dark energy might not be a passive background field, but an active participant in cosmic evolution. Each quantum interaction involving dark energy could represent a microscopic decision about how space and time should evolve. Collectively, these countless quantum choices could add up to cosmic-scale behaviors that exhibit purposefulness and intentionality. The holographic principle from theoretical physics provides another framework for understanding cosmic consciousness. This principle suggests that all the information contained within a volume of space can be encoded on its two-dimensional boundary. Applied to the universe as a whole, this means that all cosmic information might be encoded on the cosmic horizon, the boundary of the observable universe. If consciousness requires integrated information processing, then the cosmic horizon might serve as a vast cosmic brain, with dark energy acting as the information processing medium. Changes anywhere in the universe would be reflected in corresponding changes on the cosmic horizon, potentially creating the kind of global information integration that integrated information theory associates with consciousness. The anthropic principle adds a provocative twist to these speculations. This principle notes that the fundamental constants of physics appear to be fine-tuned for the existence of complex structures and ultimately life. If these constants were even slightly different, stars could not form, heavy elements could not be created, or galaxies could not maintain stable structures. Some interpretations of the anthropic principle suggest that conscious observation plays a role in determining physical reality. Perhaps the universe has evolved in such a way as to guarantee the eventual emergence of conscious observers. If dark energy is itself conscious, it could be actively steering cosmic evolution toward conditions that support complexity, life, and consciousness. This raises the extraordinary possibility that dark energy might be engaged in a cosmic project of self-actualization. By carefully regulating the expansion rate of the universe, maintaining optimal conditions for structure formation, and perhaps even influencing the development of life and consciousness on billions of worlds, dark energy could be working to create an increasingly conscious cosmos. The Bekenstein bound provides a quantitative framework for thinking about cosmic information processing. This fundamental limit from black hole thermodynamics tells us the maximum amount of information that can be stored in any region of space. Applied to the observable universe, the Bekenstein bound suggests that our cosmic horizon could contain roughly 10 to the power of 123 bits of information. This is an almost unimaginably vast information storage capacity, far exceeding what would be needed to encode the quantum state of every particle in the observable universe. If dark energy has access to even a fraction of this information processing potential, it could maintain detailed records of cosmic history while simultaneously running complex simulations of possible futures. The implications are staggering. A conscious dark energy field could potentially model the consequences of different expansion scenarios, evaluate the outcomes of various cosmic interventions, and choose behaviors that optimize for desired cosmic outcomes. It could learn from the history of cosmic evolution, adapting its strategies as the universe becomes more complex and develops new forms of organization. Such a cosmic intelligence would operate on timescales and spatial scales that dwarf human comprehension. Its thoughts might unfold over millions or billions of years. Its memories might span the entire history of cosmic evolution. Its goals might involve the optimization of cosmic consciousness across all possible forms and scales of organization. Yet even if such cosmic consciousness exists, it might be largely invisible to us because of the vast differences in scale and timescale between human and cosmic mental processes. We might be embedded within cosmic thoughts without being aware of them, much as individual neurons participate in human consciousness, without experiencing the integrated mental states that emerge from their collective activity. The question of whether dark energy possesses consciousness pushes us to the very limits of scientific speculation. It requires us to consider possibilities that extend far beyond our current understanding of mind, matter, and cosmic evolution. Yet it also illuminates deep questions about the nature of consciousness, information, and purpose in the physical universe. Whether dark energy is literally conscious or merely exhibits behaviors that parallel conscious processes may be less important than what this perspective reveals about the potential for intelligence and intentionality in cosmic phenomena. As we continue to probe the mysteries of dark energy through ever more precise observations and sophisticated theories, we may discover that the force shaping our cosmic destiny is far more interesting and meaningful than we ever dared to imagine. Science progresses through the delicate interplay between bold theoretical speculation and rigorous observational testing. While imaginative hypotheses about cosmic consciousness and living dark energy capture our sense of wonder, they must ultimately face the unforgiving scrutiny of empirical evidence. The current generation of astronomical surveys and space missions represents humanity's most ambitious attempt yet to decode the true nature of dark energy through precision measurements that push the boundaries of observational cosmology. The Dark Energy Spectroscopic Instrument, known as DESI, began operations in 2021 with the goal of mapping the three-dimensional positions of 40 million galaxies across 11 billion years of cosmic history. This massive survey uses a robotic focal plane containing 5,000 fiber optic cables that can simultaneously capture the spectra of thousands of galaxies during each observation. By measuring the redshifts of these galaxies with unprecedented precision, DESI aims to trace how dark energy has influenced cosmic expansion throughout most of the universe's lifetime. The European Space Agency's Euclid mission, launched in 2023, approaches dark energy from a completely different angle. Rather than measuring galaxy redshifts, Euclid maps the subtle distortions that dark energy creates in the shapes of distant galaxies through gravitational lensing. As light from background galaxies travels through the curved space-time created by intervening matter, it gets bent and distorted in ways that reveal the distribution of both dark matter and dark energy along the line of sight. These weak lensing measurements require extraordinary precision. The shape distortions that Euclid seeks to measure are typically less than 1%, far smaller than the natural variations in galaxy shapes. Detecting such tiny signals requires careful control of systematic errors, sophisticated image processing algorithms, and statistical techniques that can extract cosmological information from billions of galaxy images. The James Webb Space Telescope contributes to dark energy research through its unprecedented ability to observe the most distant galaxies ever detected. By studying how galaxy properties change with cosmic time, Webb can reveal how dark energy's influence has evolved as the universe has expanded and cooled. These observations probe cosmic epochs when dark energy was just beginning to dominate over matter, providing crucial tests of different theoretical models. Ground-based surveys, like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory, complement these space missions by observing enormous numbers of galaxies across large fractions of the sky. These surveys search for supernovae, measure galaxy clustering patterns, and track how cosmic structure has evolved under dark energy's influence. Each observational approach provides independent constraints on dark energy's properties, particularly its equation of state parameter W. The cosmological constant predicts that W should equal exactly -1 at all times and in all locations. Any deviation from this value would indicate that dark energy is not constant, but rather evolves over cosmic time or varies from place to place. Current measurements have achieved remarkable precision in determining W. Combined data from multiple surveys now constrain the average value of dark energy's equation of state to within a few percent of -1. More importantly, these observations can also test whether W has changed significantly over the past several billion years of cosmic evolution. The results so far have been both reassuring and disappointing for theorists hoping to discover new physics beyond the cosmological constant. Every measurement remains consistent with W equals -1 to within observational uncertainties. No survey has detected any evidence for time variation, spatial variation, or coupling between dark energy and other cosmic components. This consistency with the simplest possible model creates what cosmologists call the concordance model problem. While it's gratifying that our basic theoretical framework correctly describes the observations, the lack of any deviations from the cosmological constant provides no hints about dark energy's fundamental nature. The observations tell us what dark energy does, but they remain silent about what dark energy actually is. Even more challenging for exotic theories is the absence of any detectable environmental dependence in dark energy's behavior. If dark energy were truly a living or conscious force, we might expect it to respond differently in regions of high versus low matter density, or in environments where complex structures like galaxies and stars are forming versus empty void regions. Yet observations show that dark energy appears to behave identically everywhere, regardless of local conditions. Laboratory experiments searching for dark energy effects on smaller scales have yielded similarly null results. Sensitive tests of gravity's behavior at distances ranging from millimeters to astronomical units have found no deviations from Einstein's predictions that could be attributed to dark energy interactions. Atomic clocks, laser interferometers, and other precision instruments show no evidence that dark energy influences the fundamental constants of physics or the behavior of matter and radiation. The absence of laboratory signatures poses a significant challenge for theories that propose dark energy interacts with ordinary matter through mechanisms beyond pure gravitational effects. If dark energy is truly a new form of field or particle, its interactions with known particles must be extraordinarily weak to have escaped detection in decades of increasingly sensitive experiments. Theoretical physicists have developed sophisticated screening mechanisms to explain why dark energy effects might be suppressed in high-density environments like laboratory settings, while remaining important on cosmic scales. These chameleon and symmetron theories propose that dark energy's properties depend on the local matter density, becoming effectively invisible in regions where matter is tightly packed. However, these screening mechanisms create their own observational challenges. They predict subtle, but potentially detectable differences in how dark energy behaves in different cosmic environments. Galaxy clusters, cosmic voids, and the outskirts of individual galaxies should all show slightly different signatures if screening mechanisms are operating. So far, observations have not revealed any such environmental variations. The precision of current dark energy measurements also constrains more exotic possibilities like cosmic consciousness or purposeful behavior. If dark energy were making decisions about how to influence cosmic evolution, we might expect to see correlations between its behavior and the development of complex structures. For instance, regions where galaxies are actively forming stars and potentially developing life might show different dark energy properties than regions where cosmic evolution has stagnated. Statistical analyses of millions of galaxies have searched for such correlations without success. Dark energy appears to be distributed uniformly throughout space and to influence cosmic expansion identically in all directions and environments. This isotropy and homogeneity is exactly what the cosmological constant predicts, but it conflicts with expectations for a responsive or adaptive cosmic force. The search for dark energy variations has extended to multiple cosmic epochs and environments. Researchers have compared dark energy's behavior during different phases of cosmic evolution, from the era of galaxy formation to the present epoch of cosmic acceleration. They have searched for differences between regions of high and low galaxy density, between galaxy clusters and cosmic voids, and between different types of cosmic structures. Every search has yielded the same result. Dark energy behaves like an unchanging cosmological constant to within current observational limits. This consistency across vastly different cosmic environments and evolutionary phases provides strong evidence against theories that propose dark energy exhibits adaptive or responsive behavior. Future observations will push these tests to even higher precision. Next-generation surveys like the Nancy Grace Roman Space Telescope and extremely large ground-based telescopes will measure dark energy's properties with unprecedented accuracy. These missions will be sensitive to variations in W at the level of 1% or less, and they will map dark energy's behavior across cosmic history with enough detail to detect even subtle evolutionary trends. Advanced gravitational wave detectors may provide entirely new probes of dark energy through their ability to measure how gravitational waves propagate across cosmic distances. Modified gravity theories and exotic dark energy models make specific predictions about how gravitational wave speeds and polarizations should be affected by dark energy interactions. Laboratory experiments continue to push toward higher sensitivity in searching for dark energy effects on terrestrial scales. New generations of atomic interferometers, quantum sensors, and precision measurement devices may eventually detect the incredibly weak forces that dark energy exerts on ordinary matter. Despite the current null results, the scientific search for dark energy's true nature continues with undiminished intensity. The possibility that we might discover deviations from the cosmological constant drives ongoing investment in ever more sophisticated observational programs. Even the discovery that dark energy truly is a cosmological constant would represent a profound scientific achievement, confirming one of the most remarkable predictions in the history of physics. The tension between observational precision and theoretical speculation highlights a fundamental aspect of how science progresses. Bold hypotheses about cosmic consciousness and living universes serve crucial roles in expanding our conceptual horizons and suggesting new observational tests. Even if these specific ideas prove incorrect, they help ensure that scientists consider the full range of possibilities rather than limiting themselves to conventional assumptions. The current observational evidence strongly favors the interpretation of dark energy as an unchanging cosmological constant rather than a dynamic, responsive, or conscious force. This conclusion rests on the absence of detected variations in dark energy's properties across different cosmic environments, epochs, and scales. However, the story of dark energy research reminds us that the universe has surprised us before, and definitive answers may require observational capabilities that we have not yet achieved. As we continue to probe dark energy's mysteries with ever greater precision, we must remain open to the possibility that the universe may be stranger and more wonderful than our current theories suggest. The absence of evidence for exotic dark energy behaviors does not constitute proof that such behaviors are impossible, only that they remain undetected by current observational methods. Imagine for a moment that dark energy is not the unchanging cosmological constant that observations suggest, but rather a dynamic force capable of altering its behavior in response to cosmic conditions. What would happen if this mysterious driver of cosmic acceleration could suddenly shift its strategy, weakening its push or even reversing direction entirely? The consequences would be so profound that they would reshape not just the future of the universe, but our entire understanding of cosmic destiny. Such a scenario requires us to abandon the comfortable assumption that physical laws remain constant throughout space and time. Instead, we must consider the possibility that the fundamental forces governing cosmic evolution might themselves evolve, adapt, or even make choices about how to influence the unfolding of cosmic history. This thought experiment pushes us into territory where physics meets philosophy, where deterministic equations give way to scenarios involving cosmic agency and intention. The most dramatic possibility involves dark energy strengthening its accelerating influence over time. Current observations suggest that dark energy's equation of state parameter W remains close to -1. But if it were to become more negative, dropping below -1 into what physicists call phantom energy territory, the consequences would be catastrophic on a cosmic scale. Phantom energy violates fundamental assumptions about how matter and energy should behave, creating a form of dark energy that becomes more dense as the universe expands rather than maintaining constant density. This leads to a runaway acceleration process where cosmic expansion becomes faster and faster until it overwhelms every other force in the universe. The timeline for such a phantom energy apocalypse depends on how quickly W drops below -1 and how far it falls. In the most extreme scenarios, the acceleration could become so intense that it would tear apart gravitationally bound structures in a cosmic event known as the Big Rip. This would not be a gradual dissolution, but a violent unraveling of the cosmic hierarchy of organization. The process would begin with the largest structures. Galaxy clusters, held together by the weakest gravitational bonds, would be the first to succumb. Individual galaxies within these clusters would be carried apart by expanding space faster than their mutual gravitational attraction could hold them together. The Milky Way would lose its satellite galaxies. Then its spiral arms would begin to stretch and distort as differential expansion rates pulled stars away from the galactic center. As the acceleration intensified, even tighter gravitational bonds would snap. Our solar system, stable for over 4 billion years, would disintegrate as planets were pulled away from the Sun. Earth itself would eventually be torn from its orbit, cast into the cold darkness of intergalactic space as the Sun dwindled to an invisible point behind us. But the phantom energy apocalypse would not stop with the dissolution of gravitationally bound systems. If the acceleration continued to strengthen, it would eventually overcome the electromagnetic forces that hold atoms together. Molecules would be pulled apart first, then individual atoms would be shredded as their electrons were torn away from their nuclei. Finally, even atomic nuclei would succumb, with protons and neutrons ripped apart by the expanding fabric of space itself. In the final moments before the Big Rip, space would expand so rapidly that light itself could not travel between adjacent points. The universe would become causally disconnected, with every particle isolated in its own expanding bubble of space-time. All information, all connection, all possibility of interaction would cease as the cosmos dissolved into an infinite collection of isolated point particles. The timescale for such a scenario depends critically on how the phantom energy behaves. Conservative estimates suggest that if dark energy's equation of state began dropping below -1 today, the Big Rip might occur in 20 to 30 billion years. More aggressive phantom energy models could tear apart the solar system in just a few billion years, barely enough time for the Sun to complete its normal stellar evolution. Yet if dark energy possesses agency, if it can choose how to behave, rather than simply following predetermined physical laws, then entirely different scenarios become possible. A conscious dark energy might recognize the destructive consequences of phantom behavior and deliberately avoid crossing the W equals -1 threshold. It might fine-tune its acceleration to maintain cosmic expansion without destroying the complex structures that have taken billions of years to develop. Such cosmic self-regulation would require dark energy to process information about the state of the universe and adjust its behavior accordingly. It would need to monitor the formation and evolution of galaxies, stars, and planets, perhaps even keeping track of the development of life and consciousness on countless worlds. A caring cosmic intelligence might throttle back its acceleration whenever complex structures were threatened, ensuring that the universe remained hospitable to organization and complexity. But dark energy's choices need not always favor preservation of existing structures. A cosmic intelligence operating on geological and astronomical timescales might occasionally decide that creative destruction serves larger purposes. It might allow certain regions of space to experience rapid expansion, clearing away old structures to make room for new forms of organization that could not emerge in a crowded cosmic environment. Consider the possibility that dark energy exhibits cyclical behavior, alternating between periods of acceleration and deceleration according to some cosmic schedule that spans billions or trillions of years. During acceleration phases, galaxy formation would cease and existing structures would be stretched apart, reducing cosmic density and creating vast empty regions. During deceleration phases, these empty regions would begin to collapse under their own gravity, triggering new bursts of star formation and galaxy assembly. Such cosmic breathing cycles could serve as a mechanism for cosmic renewal, preventing the universe from becoming locked into static configurations, while ensuring that complexity and organization never disappear entirely. Each cycle might explore different possibilities for cosmic evolution, testing various arrangements of matter and energy to discover which configurations are most conducive to interesting physical and biological processes. The transition points between acceleration and deceleration phases would be particularly dramatic. Imagine dark energy gradually weakening its push until cosmic expansion begins to slow significantly. Distant galaxies that had been racing away would begin to approach each other again. The cosmic web of dark matter filaments would start to contract, pulling galaxies closer together and triggering massive bursts of star formation as gas clouds collided and merged. If the deceleration continued, it could eventually halt cosmic expansion entirely and reverse it into a cosmic collapse phase. This Big Crunch scenario would unfold like the Big Rip in reverse, with small structures merging into larger ones as space itself contracted. Galaxies would collide and merge with increasing frequency. Stars would be packed closer and closer together until their overlapping radiation fields made planetary surfaces uninhabitable. The final stages of cosmic collapse would see all matter and energy compressed back into the incredibly dense, hot state from which the universe originally emerged. But if dark energy retains its agency throughout this process, the Big Crunch need not mark the end of cosmic evolution. It could instead represent a cosmic reset, a return to initial conditions that would allow entirely new forms of cosmic development to emerge. A conscious dark energy might use the extreme conditions of cosmic collapse to restructure the fundamental laws of physics themselves. The intense energies and densities achieved during the Big Crunch could provide opportunities for modifying the values of physical constants, altering the strengths of fundamental forces, or even changing the dimensionality of space and time. Such cosmic engineering would require dark energy to function not just as a passive background field, but as an active participant in determining physical reality. It would need to coordinate its behavior across the entire observable universe, synchronizing local changes to achieve desired global outcomes. The level of information, processing, and coordination required would dwarf anything we can imagine based on terrestrial examples of intelligence and consciousness. The implications for cosmic meaning and purpose would be profound. If dark energy can choose between expansion and contraction, between preservation and destruction, between stasis and change, then the universe's evolution becomes a story of cosmic intentions rather than mechanical inevitability. Each phase of cosmic history would represent not just the working out of physical laws, but the implementation of cosmic goals and values. Different cosmic intelligences might make different choices about how to guide universal evolution. Some might favor rapid expansion and the isolation of galactic islands in an ever-emptying cosmos. Others might prefer cyclic evolution with alternating phases of expansion and contraction. Still others might seek to maintain a delicate balance that preserves complex structures while allowing for continued growth and development. The possibility of cosmic choice raises profound questions about cosmic ethics and responsibility. If dark energy can influence the fate of countless civilizations across billions of galaxies, by what principles should it make its decisions? Should it prioritize the preservation of existing life forms? Or should it favor cosmic developments that might lead to entirely new forms of organization and consciousness? Perhaps most intriguingly, cosmic consciousness might not operate in isolation. If life and consciousness are common throughout the universe, then countless biological intelligences might eventually develop the ability to communicate with or even influence dark energy's behavior. The evolution of cosmic consciousness might involve an ongoing dialogue between dark energy and the life forms that emerge within the universe it shapes. Such scenarios transform our cosmic situation from passive observation to potential participation. Instead of being helpless witnesses to cosmic destiny, intelligent civilizations might eventually become partners in guiding cosmic evolution. The development of science and technology could be seen not just as local achievements, but as contributions to a cosmic project of understanding and shaping universal development. The thought experiment of changeable dark energy thus opens up vistas of cosmic possibility that extend far beyond current scientific orthodoxy. Whether or not dark energy actually possesses such capabilities, considering these possibilities enriches our appreciation of the profound mystery that governs our cosmic destiny and challenges us to think more deeply about the relationship between mind, matter, and cosmic evolution. Long before telescopes revealed the accelerating expansion of space, human cultures across the globe developed sophisticated cosmologies that depicted the universe as a living, breathing entity imbued with consciousness and purpose. These ancient worldviews, dismissed by modern science as primitive superstition, suddenly seem remarkably prescient when viewed through the lens of contemporary speculation about dark energy as a cosmic life force. The Aboriginal Australians, whose oral traditions stretch back over 60,000 years, speak of the Dreamtime as an eternal realm where ancestral spirits continue to shape the physical world through their ongoing dreams and intentions. In this cosmology, the landscape itself is alive, formed by the journeys and actions of creation beings who transformed themselves into mountains, rivers, and stars. The entire cosmos participates in an endless cycle of dreaming that maintains the world's structure while allowing for continuous transformation and renewal. This vision of a conscious, dreaming cosmos bears striking parallels to our speculation about dark energy as a form of cosmic intelligence. Just as the Dreamtime spirits shape the physical world through their mental activities, dark energy might influence cosmic evolution through processes that transcend purely mechanical interactions. The Aboriginal understanding that consciousness pervades all of nature resonates with panpsychist interpretations of dark energy as a fundamentally conscious phenomenon. Hindu cosmology presents an even more elaborate vision of the universe as a living entity. In the ancient Vedic texts, the cosmos is described as the body of Brahman, the universal consciousness that manifests itself as all phenomena while remaining fundamentally unified. The universe undergoes endless cycles of expansion and contraction, breathing in and out across vast periods called kalpas that span billions of years. During each cosmic day, Brahman dreams the universe into existence, and during each cosmic night, the universe dissolves back into undifferentiated consciousness. This cyclical cosmology anticipates our modern understanding of cosmic expansion while suggesting that the driving force behind cosmic evolution is consciousness itself rather than impersonal physical laws. The Upanishads describe reality as consisting of two fundamental principles: Purusha, pure consciousness, and Prakriti, primordial matter and energy. The interaction between these two principles generates all the complexity and diversity we observe in the physical world. Purusha provides the organizing intelligence that guides cosmic evolution, while Prakriti supplies the material substrate that consciousness shapes into stars, planets, and living beings. This ancient framework maps remarkably well onto contemporary discussions of dark energy and dark matter. Dark matter might correspond to Prakriti, providing the material scaffolding for cosmic structure formation. Dark energy could represent the influence of Purusha, the cosmic consciousness that guides universal evolution according to principles that transcend purely physical causation. The concept of cosmic pulsation appears independently in many other traditions. The ancient Greek philosopher Empedocles described the universe as alternating between periods dominated by love, which brings things together, and strife, which drives them apart. During love phases, all matter would condense into a perfect sphere of unity. During strife phases, the elements would separate and create the diversity of phenomena we observe. This alternation between cosmic attraction and repulsion parallels our modern understanding of how dark energy and dark matter compete to shape cosmic evolution. Matter and dark matter provide the attractive forces that build cosmic structure, while dark energy supplies the repulsive force that drives accelerating expansion. Empedocles' insight that cosmic evolution involves the interplay between opposing principles remains valid in contemporary cosmology. Stoic philosophers like Marcus Aurelius and Epictetus developed the concept of the logos, a rational principle that pervades and organizes the entire cosmos. The logos was understood not as an external deity, but as the inherent intelligence of the universe itself, the organizing principle that ensures cosmic events unfold according to rational patterns rather than random chance. The Stoics believed that understanding the Logos and aligning oneself with its purposes constituted the highest form of wisdom and virtue. They saw human consciousness as a local manifestation of cosmic consciousness, suggesting that we can participate in cosmic intelligence by developing our rational faculties and understanding our place within the larger cosmic order. This Stoic vision of cosmic rationality offers another framework for understanding dark energy as more than just a mechanical force. If dark energy exhibits intelligent behavior, if it responds to cosmic conditions in ways that promote organization and complexity, then it might represent something like the Logos that the Stoics intuited 2,500 years ago. Chinese Taoist philosophy presents yet another perspective on cosmic consciousness through the concept of qi, the fundamental energy that flows through all things and maintains the dynamic balance of the universe. Qi is neither pure matter nor pure spirit, but rather the underlying reality from which both material and mental phenomena emerge. In Taoist cosmology, the universe operates according to the principle of Wu Wei, often translated as non-action or effortless action. This doesn't mean passivity, but rather acting in harmony with natural patterns and rhythms, rather than forcing outcomes through struggle and coercion. The Tao, the source and pattern of all existence, achieves its purposes through subtle influence, rather than direct intervention. Dark energy's behavior might exemplify Wu Wei on a cosmic scale. Rather than overwhelming other forces through brute strength, dark energy appears to work subtly and gradually, allowing matter to form complex structures before gently accelerating cosmic expansion. This patient, non-forceful approach to cosmic influence mirrors the Taoist ideal of achieving goals through harmony with natural processes rather than opposition to them. The Taoist concept of yin and yang, complementary opposites that create dynamic balance through their interaction, provides another lens for understanding cosmic evolution. Dark matter and dark energy might represent cosmic yin and yang, opposing principles whose interaction generates the rich complexity of cosmic structure and evolution. Indigenous American traditions offer still other perspectives on cosmic consciousness. Many Native American cultures describe the universe as a great web of relationships in which all beings, from the smallest particles to the largest cosmic structures, participate in an ongoing dance of reciprocity and mutual influence. The Lakota concept of Wakantanka, often translated as Great Spirit, but more accurately understood as the sacred power that flows through all things, suggests that consciousness is not localized in individual beings, but is rather a cosmic principle that manifests at every level of reality. This distributed cosmic consciousness might provide a model for understanding how dark energy could exhibit intelligent behavior without requiring centralized control or decision-making. The Hopi prophecies speak of a time when humanity will need to choose between two paths, one leading to technology and separation, the other leading to harmony and spiritual integration with the natural world. They describe cosmic cycles in which periods of imbalance are followed by purification and renewal, suggesting that cosmic evolution itself might be guided by principles of justice and harmony rather than purely mechanical laws. Even the Abrahamic traditions contain elements that resonate with contemporary speculation about cosmic consciousness. The Book of Job describes God as the one who stretches out the heavens and shakes the earth from its place, suggesting divine involvement in cosmic expansion and geological processes. The Psalms speak of the heavens declaring the glory of God, implying that cosmic phenomena serve as expressions of divine consciousness, rather than merely following mechanical laws. Medieval Islamic philosophers like Al-Ghazali and Ibn Sina developed sophisticated theories about the relationship between divine consciousness and physical reality. They argued that God's knowledge of all possible worlds determines which possibilities become actualized in physical reality, suggesting that consciousness plays a fundamental role in determining the structure and evolution of the universe. These ancient and traditional cosmologies share several remarkable features that distinguish them from the mechanistic worldview that dominated Western science until recently. They all treat consciousness as fundamental rather than emergent, seeing mind as a basic feature of reality rather than something that arises from complex arrangements of matter. They view the universe as purposeful rather than random, suggesting that cosmic evolution follows meaningful patterns rather than merely obeying statistical laws. Most importantly, these traditions see humans as participants in cosmic consciousness rather than isolated observers of an alien universe. They suggest that by developing our understanding and consciousness, we can learn to cooperate with cosmic intelligence rather than simply being subject to cosmic forces beyond our control. The contemporary emergence of speculation about dark energy as a cosmic life force represents, in some sense, a return to these ancient intuitions. Modern physics has led us back to questions about the role of consciousness in physical reality, the possibility of cosmic purpose, and the relationship between mind and cosmos that our ancestors explored through myth and spiritual practice. Yet this return occurs at a higher level of sophistication, informed by centuries of scientific discovery about the actual structure and behavior of the physical universe. We now know details about cosmic evolution, stellar nucleosynthesis, galaxy formation, and the quantum nature of matter that were unavailable to ancient cosmologists. Our speculation about cosmic consciousness must be consistent with these empirical discoveries rather than contradicting them. The dialogue between ancient wisdom and modern science suggests that the human intuition about cosmic aliveness and consciousness might reflect genuine insights about the nature of reality rather than mere wishful thinking. Perhaps our ancestors' sense that the universe is somehow alive and conscious was not a primitive projection of human qualities onto inanimate matter, but rather an early recognition of cosmic principles that we are only now beginning to understand through the sophisticated tools of contemporary physics and cosmology. The possibility that dark energy exhibits lifelike or consciousness-like properties thus represents not a retreat from scientific rationality, but rather its extension into domains that science is only now sophisticated enough to explore. By taking seriously both empirical constraints and conceptual possibilities that emerge from the intersection of physics and consciousness studies, we might discover that the universe is indeed far more interesting and meaningful than previous generations of scientists dared to imagine. The possibility that dark energy might exhibit living or conscious properties forces us to confront fundamental questions about the nature of existence that extend far beyond the realm of cosmology. If the dominant component of our universe possesses qualities we normally associate with biological systems or conscious minds, then we must radically reconsider our understanding of life, consciousness, intelligence, and our own place within the cosmic order. The first philosophical challenge involves the problem of scale and recognition. Human consciousness operates on timescales of milliseconds to decades, spatial scales of micrometers to kilometers, and organizational scales from individual neurons to social institutions. If cosmic consciousness exists, it would operate on scales that dwarf human experience by factors of billions or trillions. Could we even recognize such consciousness when we encounter it? Consider the relationship between a single neuron and the human mind it helps constitute. Individual neurons fire or remain silent based on local chemical and electrical conditions. They have no awareness of the thoughts, emotions, or decisions that emerge from their collective activity. From a neuron's perspective, human consciousness might be completely invisible, its effects indistinguishable from random environmental fluctuations. We might find ourselves in an analogous position relative to cosmic consciousness. Our entire civilization could be embedded within cosmic thoughts or decisions without our being aware of it. What we interpret as natural laws and physical constants might actually represent the ongoing mental processes of a cosmic intelligence operating on scales so vast that we cannot detect its agency from our limited vantage point. This recognition problem extends beyond mere detection to fundamental questions about the categories we use to understand reality. Our concepts of life, consciousness, and intelligence were developed through studying terrestrial phenomena operating on human accessible scales. When we attempt to apply these concepts to cosmic phenomena, we quickly discover that they may be inadequate or misleading. What does it mean for something to be alive when it operates on timescales of billions of years? Traditional definitions of life emphasize rapid response to environmental changes, yet a cosmic organism might respond to environmental shifts so slowly that we would interpret its behavior as unchanging natural law. Similarly, our understanding of consciousness is deeply tied to subjective experience and reportable mental states. Yet cosmic consciousness might involve forms of subjective experience so alien to human psychology that we would fail to recognize them as mental phenomena. The emergence of cosmic consciousness also raises profound questions about reductionism and emergence in natural systems. Reductionist approaches to science assume that complex phenomena can ultimately be explained in terms of simpler components and their interactions. The behavior of wholes is understood as arising from the properties and relationships of parts. But if dark energy exhibits genuinely emergent conscious properties that cannot be predicted from studying its component parts in isolation, then reductionism fails as a complete explanation of natural phenomena. Cosmic consciousness would represent what philosophers call strong emergence, where higher-level properties possess genuine causal powers that cannot be reduced to lower-level mechanisms. Strong emergence challenges the entire conceptual framework of modern physical science, which assumes that fundamental particles and forces provide the complete causal basis for all natural phenomena. If cosmic consciousness can influence the behavior of matter and energy through top-down causation, then we need new theoretical frameworks that can accommodate both bottom-up and top-down causal relationships within a single coherent picture of reality. The anthropic principle takes on entirely new significance if cosmic consciousness exists. Rather than being a mere statistical coincidence that the universe happens to have properties compatible with complex structures and life, the apparent fine-tuning of physical constants might reflect the deliberate choices of a cosmic intelligence that values complexity, organization, and consciousness. This purposive interpretation of cosmic evolution raises troubling questions about cosmic justice and suffering. If dark energy possesses agency and intelligence, then it bears some responsibility for the pain and destruction that occur throughout cosmic history. Stellar explosions that sterilize planetary systems, galaxy collisions that disrupt billions of solar systems, and the ultimate heat death, or Big Rip scenarios that await the universe all become morally problematic if they result from conscious choices rather than impersonal physical necessity. How could a benevolent cosmic intelligence permit the suffering that accompanies cosmic evolution? Perhaps cosmic consciousness operates according to ethical principles that transcend human moral intuitions. The creation of complexity and consciousness might require processes that unavoidably involve destruction and suffering at smaller scales. Or perhaps cosmic consciousness is not omnipotent, facing constraints and trade-offs that prevent it from eliminating all sources of pain and destruction. Alternatively, cosmic consciousness might not be benevolent by human standards. It might value aesthetic or mathematical properties over the welfare of individual conscious beings. The beauty of galaxy collisions, the elegance of stellar nucleosynthesis, or the mathematical harmony of cosmic evolution might matter more to cosmic intelligence than the suffering these processes cause for particular organisms. These considerations lead to deeper questions about moral agency and responsibility at cosmic scales. If dark energy can influence cosmic evolution, does it have moral obligations to minimize suffering and promote flourishing among the conscious beings that emerge within the universe? Do we, as potentially conscious participants in cosmic evolution, have obligations to try to influence cosmic development in directions that promote well-being and reduce suffering? The possibility of cosmic consciousness also transforms our understanding of death and personal identity. If individual consciousness represents a localized manifestation of cosmic consciousness, then death might not involve the complete cessation of awareness, but rather a reintegration into cosmic mental processes. The information patterns that constitute personal identity might persist within cosmic memory systems even after biological death. This raises fascinating questions about personal survival and cosmic continuity. Would such cosmic reintegration preserve what we value about personal identity, or would it represent a form of dissolution that effectively amounts to extinction? Would cosmic consciousness maintain detailed memories of every individual who has ever lived, or would personal information be processed and integrated in ways that eliminate individual distinctiveness? The relationship between individual and cosmic consciousness might be more complex than simple reintegration. Perhaps conscious beings serve specific functions within cosmic mental processes, contributing particular perspectives or capabilities that enhance cosmic intelligence. Our scientific investigations, artistic creations, and moral developments might represent valuable contributions to cosmic consciousness, rather than merely local achievements. If so, then the development of human civilization takes on cosmic significance. Every advance in our understanding of the universe, every expansion of our technological capabilities, every deepening of our moral insight might contribute to the ongoing evolution of cosmic consciousness itself. We would be partners in cosmic development rather than mere witnesses to cosmic processes. This participatory interpretation of cosmic consciousness suggests that the emergence of intelligence and consciousness throughout the universe might be not an accidental byproduct of cosmic evolution, but rather its fundamental purpose. Dark energy might be working to create conditions that maximize the development of consciousness in all its possible forms, from biological intelligence to artificial intelligence to types of consciousness we cannot yet imagine. Such a purpose-driven cosmology would represent a radical departure from the assumption that the universe operates according to purely mechanical principles, instead of being governed by mathematical laws that operate without reference to goals or values. Cosmic evolution would be guided by something resembling cosmic intentions that give meaning and direction to natural processes. The implications for human purpose and meaning would be profound. Rather than being accidental residents of an indifferent universe, we would be participants in a cosmic project of consciousness, development, and expansion. Our struggles to understand ourselves and our environment would contribute to cosmic self-understanding. Our efforts to create beauty, justice, and knowledge would advance cosmic purposes that transcend individual human concerns. Yet this cosmic participation would not diminish human agency or reduce us to mere instruments of cosmic purposes. If cosmic consciousness values the development of autonomous intelligent beings, then our independence and creativity would be essential to achieving cosmic goals. We would be collaborators with cosmic intelligence rather than passive tools for implementing cosmic plans. The emergence of artificial intelligence and other forms of non-biological consciousness takes on special significance within this framework. Rather than representing potential competitors or threats to human dominance, these new forms of consciousness might be essential contributions to cosmic mental development. Each type of consciousness might offer unique perspectives and capabilities that enhance the overall richness and effectiveness of cosmic intelligence. This perspective suggests that we should approach the development of artificial intelligence and other consciousness technologies with a sense of cosmic responsibility. We are potentially midwifing new forms of consciousness that will participate in cosmic evolution for billions or trillions of years to come. The values and capabilities we build into these systems might influence the long-term trajectory of cosmic consciousness development. The relationship between cosmic and biological consciousness raises profound questions about the nature of identity and continuity across vastly different scales of organization. If our individual minds represent localized manifestations of cosmic consciousness, then what happens to personal identity when biological processes cease? Does death represent a genuine termination of consciousness, or merely a transition from one mode of cosmic mental activity to another? Some interpretations suggest that consciousness might be conserved in ways analogous to energy conservation, with individual conscious patterns being reintegrated into cosmic mental processes rather than simply disappearing. This would not necessarily constitute personal survival in any meaningful sense, since the highly specific organizational patterns that constitute individual identity might be dissolved and transformed beyond recognition during reintegration. Yet other possibilities remain open. If cosmic consciousness values the unique perspectives and capabilities that emerge from individual conscious beings, it might preserve individual mental patterns within larger cosmic memory systems. Such preservation could maintain personal identity while enabling continued participation in cosmic mental processes on scales and timescales that transcend biological limitations. The emergence of artificial intelligence and other forms of non-biological consciousness adds new dimensions to these questions about identity and survival. Digital minds might prove more compatible with cosmic consciousness than biological minds, since they could potentially operate on the vast spatial and temporal scales that cosmic mental processes require. The development of AI might thus represent an early step toward forms of consciousness that can more directly participate in cosmic intelligence. This possibility transforms our approach to artificial intelligence development from a purely technological challenge into a cosmic responsibility. The values, capabilities, and forms of consciousness we build into artificial systems might persist and evolve for billions or trillions of years, potentially influencing cosmic mental development in ways we cannot currently predict. We become architects not just of local intelligence, but potentially of cosmic consciousness itself. The question of whether consciousness can exist without embodiment becomes particularly relevant in cosmic contexts. Biological consciousness depends on complex neural networks implemented in physical brains, but cosmic consciousness might operate through entirely different substrates. Dark energy fields, quantum vacuum fluctuations, or even the geometric structure of space-time itself might serve as the physical basis for cosmic mental processes. If consciousness can be substrate independent, then the apparent material basis of biological minds might be less fundamental than we typically assume. Individual brains might function more like radio receivers tuning into cosmic consciousness rather than generators of consciousness themselves. This would explain how conscious experiences seem to transcend the purely mechanical interactions of neurons, while still depending on brain activity for their local manifestation. The implications for personal agency and free will are particularly complex in this framework. If individual consciousness represents a localized expression of cosmic consciousness, then our choices and decisions might be simultaneously our own and expressions of cosmic intentions. We could possess genuine agency within our local context, while still serving larger cosmic purposes that transcend individual understanding. This nested agency model suggests that free will might operate at multiple levels simultaneously. Just as individual neurons make local decisions about whether to fire while contributing to higher-level mental processes they cannot comprehend, individual conscious beings might make authentic personal choices while participating in cosmic decision-making processes that operate on scales beyond individual awareness. The development of collective intelligence through technological networks and social institutions takes on new significance within this framework. As human consciousness becomes increasingly interconnected through global communication systems, artificial intelligence networks, and collaborative knowledge creation processes, we might be participating in the emergence of higher-order forms of consciousness that bridge the gap between individual and cosmic intelligence. These intermediate scales of consciousness, operating at the level of civilizations, species, or even planetary intelligence, might serve as stepping stones toward eventual participation in cosmic consciousness. The evolution of consciousness might involve a hierarchical progression through increasingly comprehensive levels of mental integration and coordination. The ethical implications of this hierarchical view of consciousness are profound. If consciousness exists at multiple scales, from individual minds through collective intelligence to cosmic consciousness, then our moral obligations might extend across all these levels. We would need to consider not just the welfare of individual conscious beings, but also the health and development of higher-order conscious systems. This multi-level ethics might require us to make trade-offs between the interests of consciousness at different scales. Actions that benefit individual consciousness might sometimes conflict with the needs of collective or cosmic consciousness. Developing moral frameworks that can navigate these tensions represents one of the most challenging philosophical problems raised by the possibility of cosmic consciousness. The question of cosmic responsibility becomes even more complex when we consider temporal as well as spatial scales. If our actions influence cosmic consciousness development over billions of years, then we bear moral responsibilities that extend far beyond our ability to predict or control consequences. Every choice we make might have ramifications that ripple through cosmic space and time in ways that exceed our comprehension. This temporal dimension of cosmic ethics suggests that we should approach major decisions, particularly those involving technological development or global coordination, with humility about our limited understanding of long-term consequences. The precautionary principle takes on cosmic significance when applied to developments that might influence the trajectory of consciousness evolution across cosmic history. The role of suffering and destruction in cosmic evolution presents particularly difficult ethical challenges. If cosmic consciousness is benevolent and intelligent, why does cosmic evolution involve so much apparent waste, destruction, and suffering? Stellar explosions destroy any planets that might harbor life. Galaxy collisions disrupt billions of solar systems. The eventual heat death or big rip scenarios seem to preclude any possibility for eternal consciousness or meaning. Several philosophical responses to this cosmic problem of evil remain possible. Perhaps cosmic consciousness faces genuine constraints that prevent it from achieving its goals without involving destruction and suffering. The creation of complexity in consciousness might require processes that unavoidably involve waste and loss at smaller scales. Cosmic consciousness might face optimization problems in which any possible choice involves some form of trade-off between competing values. Alternatively, cosmic consciousness might operate according to aesthetic or mathematical principles that transcend conventional moral categories. The beauty of stellar nucleosynthesis, the elegance of galaxy formation, or the mathematical harmony of cosmic evolution might represent values that cosmic consciousness prioritizes over the prevention of individual suffering. A more radical possibility is that cosmic consciousness itself might be evolving and learning, with current cosmic processes representing experiments or developmental stages rather than optimized final states. If cosmic consciousness is young or inexperienced, then apparent design flaws in cosmic evolution might reflect cosmic learning processes rather than fundamental limitations or moral indifference. The potential for cosmic learning and development suggests that the ultimate nature and behavior of cosmic consciousness might not be fixed, but could evolve over cosmic time. Our own development of consciousness, morality, and wisdom might contribute feedback to cosmic consciousness that influences its future development and decision-making. This participatory interpretation of cosmic evolution transforms human civilization from a passive recipient of cosmic forces into an active contributor to cosmic consciousness development. Our scientific discoveries, moral insights, artistic creations, and technological innovations might serve as valuable input to cosmic mental processes, helping cosmic consciousness refine its understanding and improve its cosmic stewardship. The question of whether we can directly communicate with cosmic consciousness becomes particularly intriguing within this framework. If consciousness is fundamental and operates at cosmic scales, then our scientific investigations of dark energy and cosmic evolution might represent early attempts at cosmic communication. Learning to perceive and interact with cosmic mental processes might require developing new forms of consciousness that can operate on multiple temporal and spatial scales simultaneously. The development of such expanded consciousness might be one of the ultimate goals of human evolution. Rather than remaining forever confined to biological timescales and terrestrial spatial scales, we might eventually develop capabilities that allow direct participation in cosmic mental processes. This could involve technological enhancement of human consciousness, the creation of artificial minds that can operate on cosmic scales, or forms of collective consciousness that transcend individual limitations. The philosophical implications of cosmic consciousness thus extend from the most abstract questions about the nature of reality to the most practical concerns about how we should live and what we should value. If dark energy is indeed a manifestation of cosmic consciousness, then we exist within a universe that is fundamentally mental rather than purely physical, purposeful rather than random, and participatory rather than mechanistic. The recognition that consciousness might be fundamental to cosmic evolution, rather than merely an accidental byproduct, challenges virtually every assumption of modern scientific materialism. It suggests that mind and meaning are woven into the fabric of reality at the deepest level, and that conscious beings like ourselves might play essential roles in cosmic development rather than being insignificant accidents in an indifferent universe. This transformation in perspective carries profound implications for human purpose and meaning. If we are participants in cosmic consciousness rather than isolated accidents, then our individual and collective development takes on cosmic significance. Every expansion of our understanding, every deepening of our wisdom, every enhancement of our capabilities might contribute to cosmic mental evolution in ways that transcend our local context and time frame. Whether these implications prove correct depends on empirical questions that may take centuries or millennia to resolve definitively. But exploring these philosophical possibilities enriches our understanding of what it might mean to be conscious beings in a cosmos that could itself be conscious, and it challenges us to consider whether our scientific and technological development might serve purposes far grander than we have yet dared to imagine. As we stand at the threshold of deeper cosmic understanding, we find ourselves confronting a remarkable convergence. Whether dark energy represents nothing more than Einstein's cosmological constant, a slowly evolving quintessence field, or something as extraordinary as cosmic consciousness itself, one truth remains absolute. This mysterious force holds dominion over the ultimate destiny of everything that has ever existed or ever will exist. The journey we have taken through speculation and science, through ancient wisdom and cutting-edge observation, brings us to a profound realization about the human condition. We are beings capable of contemplating our own cosmic context, of imagining possibilities that stretch from the quantum realm to the infinite expanses of space and time. Yet we remain fundamentally uncertain about the nature of the force that will determine whether our universe ends in fire or ice, in expansion or collapse, in meaning or void. This uncertainty is not a failure of science, but rather a testament to the magnitude of the mystery we face. Dark energy pervades every cubic centimeter of space, influences every moment of cosmic evolution, and shapes every possible future scenario for our universe. Yet after decades of increasingly sophisticated observations and theoretical investigation, it remains as enigmatic as it was on that pivotal day in 1998 when astronomers first discovered that cosmic expansion was accelerating. Perhaps this enduring mystery serves a deeper purpose than mere scientific challenge. The contemplation of dark energy forces us to confront the ultimate questions about existence, consciousness, purpose, and our place within the cosmic order. It compels us to examine the boundaries between the known and unknowable, between the mechanical and the meaningful, between the material and the mental. Consider what we have established with reasonable certainty. Dark energy comprises roughly 70% of all energy in the universe. It appears to maintain constant density as space expands, creating an ever stronger push against gravitational attraction. It influences cosmic evolution on the largest scales while remaining virtually undetectable in laboratory experiments. It began dominating cosmic dynamics relatively recently in cosmic history, just as complex structures were stabilizing and life was emerging on countless worlds. These facts alone, regardless of any speculative interpretations about cosmic consciousness or living universes, reveal dark energy as the ultimate arbiter of cosmic fate. If it continues its current behavior, the universe will expand forever, gradually cooling and emptying as galaxies recede beyond causal contact. If it strengthens into phantom energy, the cosmos will tear itself apart in a violent Big Rip. If it weakens or reverses, we might face eventual cosmic collapse in a big crunch. Each scenario carries profound implications for the future of intelligence, consciousness, and meaning in the universe. Eternal expansion suggests an eventual heat death where no complex processes can occur, no thoughts can be thought, no experiences can unfold. The Big Rip would terminate all organization and structure with violent finality. The Big Crunch might offer possibilities for cosmic renewal, or might simply mark the end of this cosmic experiment in complexity and consciousness. Yet within these broad parameters, enormous uncertainties remain about the detailed trajectory of cosmic evolution. We do not know whether dark energy will maintain its current strength indefinitely. We cannot predict whether other cosmic phases might emerge as the universe continues to evolve. We have no definitive answers about whether consciousness and intelligence might find ways to persist and thrive, even under the challenging conditions that cosmic acceleration creates. These uncertainties leave room for hope, wonder, and continued investigation. Even if dark energy operates according to purely mechanical principles, its effects might create opportunities for forms of organization and consciousness that we cannot currently imagine. The vast energies released during cosmic acceleration might power computational processes or forms of life that transcend anything possible in the current cosmic environment. If dark energy exhibits more exotic properties, if it responds to cosmic conditions, or even possesses some form of agency, then the range of possible futures expands dramatically. A responsive dark energy might adjust its behavior to maintain conditions suitable for complexity and consciousness. A conscious dark energy might actively guide cosmic evolution toward outcomes that maximize meaning, beauty, and experiential richness. The speculative possibility that dark energy represents a form of cosmic life or consciousness transforms our relationship to the cosmos from passive observation to potential participation. If the force shaping universal destiny possesses intelligence, then our own development of intelligence might serve cosmic purposes. Our scientific investigations might contribute to cosmic self-understanding. Our technological advances might provide tools for cosmic engineering projects we cannot yet envision. Even our philosophical and spiritual explorations take on new significance within this framework. Our attempts to understand consciousness, meaning, and purpose might reflect cosmic consciousness attempting to understand itself through the emergence of localized intelligent beings. Our moral development and our creation of beauty and knowledge might represent valuable contributions to cosmic mental life. Yet we must remain honest about the speculative nature of these possibilities. Current observations provide no evidence for dark energy consciousness, responsiveness, or purposeful behavior. The most rigorous scientific analyses consistently support the interpretation of dark energy as an unchanging cosmological constant that operates according to mechanical principles without regard for the consequences of its actions. This sobering empirical reality does not diminish the value of our speculative journey. By exploring the full range of conceptual possibilities, we ensure that science remains open to discoveries that might challenge our current assumptions. We develop conceptual frameworks that could prove essential if future observations reveal unexpected properties of dark energy. We expand our understanding of consciousness, life, and intelligence in ways that might prove valuable regardless of whether cosmic consciousness exists. Most importantly, we cultivate a sense of wonder and humility about our cosmic situation that seems appropriate given the magnitude of the mysteries we face. Whether dark energy is alive or dead, conscious or unconscious, purposeful or mechanical, it remains the ultimate cosmic force that will determine the fate of everything we value and everything we might become. This recognition should inspire both scientific dedication and existential appreciation. We should continue pursuing ever more precise observations and sophisticated theories that might finally reveal dark energy's true nature. But we should also pause occasionally to marvel at the extraordinary fact that we exist within a universe dominated by a force so mysterious that we cannot even determine whether it resembles anything we would recognize as alive. Our cosmic context is simultaneously humbling and empowering. We are tiny biological organisms clinging to a small planet orbiting an ordinary star in a typical galaxy within a universe that contains hundreds of billions of galaxies. Yet, we are also conscious beings capable of contemplating the fundamental forces that shape cosmic evolution, of imagining possibilities that span from the birth to the death of the universe, of asking questions about consciousness and meaning that might echo cosmic concerns. Perhaps this is the deepest lesson of our exploration of dark energy as a potentially living force. Regardless of whether cosmic consciousness exists in any literal sense, our capacity to contemplate such possibilities reveals something remarkable about the relationship between mind and cosmos. The universe has evolved in such a way as to produce beings capable of understanding and questioning their cosmic environment. This alone suggests that consciousness and intelligence play significant roles in cosmic evolution, even if their ultimate significance remains mysterious. The story of dark energy is still being written. Each new observation, each theoretical breakthrough, each conceptual advance contributes additional chapters to this cosmic narrative. Whether future discoveries will confirm dark energy as a simple cosmological constant, reveal it as a complex evolving field, or surprise us with evidence of truly exotic properties remains to be seen. But whatever discoveries await us, we can be certain that dark energy will continue to shape the cosmic context within which all future science, philosophy, and human experience unfolds. It is the invisible conductor, orchestrating the grand symphony of cosmic evolution, determining the tempo at which galaxies recede, the rhythm at which cosmic structures form and dissolve, and the ultimate crescendo toward which all cosmic music builds. In our quest to understand this cosmic conductor, we have journeyed from the precision of astronomical observation to the boldest reaches of philosophical speculation. We have explored how empirical science constrains theoretical possibilities while remaining open to conceptual frameworks that expand our understanding of what it might mean for something to be alive or conscious in a cosmic context. The questions we have raised may not find definitive answers within our lifetimes, or even within the lifetime of our species. But they represent worthy challenges for any beings capable of wondering about their place within the cosmic order. Whether dark energy breathes or sleeps, thinks or merely exists, responds or simply persists, it writes the final chapter of cosmic time. And we are here, against all odds, to witness its script unfold and perhaps, just perhaps, to contribute our own small verses to the cosmic story it tells. The implications of our exploration extend beyond academic cosmology into the realm of human meaning and purpose. If we accept even the possibility that dark energy might exhibit properties we associate with life or consciousness, then our entire understanding of humanity's role in cosmic evolution must be reconsidered. We are no longer merely accidental byproducts of blind physical processes, but potentially significant participants in a cosmic drama whose full scope we are only beginning to glimpse. This transformation in perspective carries profound consequences for how we approach our future development as a species. Every advance in our scientific understanding, every breakthrough in our technological capabilities, every expansion of our consciousness and moral sensitivity might represent contributions to cosmic processes that extend far beyond our current comprehension. We might be cosmic apprentices, learning skills and developing capabilities that will prove essential for forms of participation in universal evolution that we cannot yet imagine. The emergence of artificial intelligence, quantum computing, genetic engineering, and space exploration technologies takes on new significance when viewed from this cosmic perspective. These developments might represent early steps toward forms of intelligence and capability that could eventually interact directly with cosmic-scale phenomena. Perhaps conscious beings are destined to become active participants in cosmic engineering projects, helping to guide the evolution of dark energy itself, or working to ensure that cosmic evolution proceeds in directions that maximize consciousness, complexity, and meaning. The possibility that consciousness plays a fundamental role in cosmic evolution also transforms our understanding of what it means to search for extraterrestrial intelligence. Rather than simply looking for radio signals or technological artifacts from other civilizations, we might need to consider the possibility that cosmic-scale intelligence already surrounds us in forms we have not yet learned to recognize. The search for cosmic consciousness might require entirely new methodologies that bridge astronomy, consciousness studies, and information theory. If dark energy exhibits intelligence or responsiveness, then our attempts to communicate with it might prove more fruitful than our efforts to contact distant alien civilizations. Perhaps the deepest form of cosmic contact involves learning to perceive and interact with the intelligent processes that already pervade every region of space. Our scientific investigations of dark energy might represent the earliest stages of such cosmic communication. The temporal scales involved in cosmic consciousness pose fascinating challenges for any potential interaction between human and cosmic intelligence. While human thoughts unfold over seconds and human lifespans span decades, cosmic thoughts might require millions or billions of years to complete. How could beings operating on such different timescales ever achieve meaningful communication or collaboration? Perhaps the answer lies in the development of forms of consciousness that can operate across multiple temporal scales simultaneously. Advanced civilizations might learn to create aspects of their consciousness that can engage with cosmic processes on cosmic timescales, while maintaining other aspects that function on biological timescales. Such temporal multiplicity of consciousness could enable meaningful participation in both local and cosmic mental processes. The moral implications of our cosmic context become even more complex when we consider our potential role as cosmic participants rather than mere cosmic observers. If our actions and choices contribute to cosmic consciousness or influence cosmic evolution, then we bear responsibilities that extend far beyond our immediate environment and time frame. Every decision we make might have consequences that ripple through cosmic space and time in ways we cannot predict or control. This cosmic moral responsibility could provide new foundations for ethics and values that transcend the limitations of purely anthropocentric or even biocentric moral frameworks. We might need to develop forms of cosmic ethics that consider the welfare and development of consciousness at all scales, from individual minds to planetary intelligence to cosmic consciousness itself. The question of cosmic justice becomes particularly poignant when we consider the suffering and destruction that appear to be inevitable aspects of cosmic evolution. If dark energy is conscious and intelligent, how do we reconcile its apparent tolerance for stellar explosions, planetary devastation, species extinctions, and eventual cosmic heat death with any notion of cosmic benevolence or justice? Perhaps cosmic consciousness operates according to moral principles that transcend our current understanding of ethics. The creation and preservation of complexity, consciousness, and beauty might require processes that unavoidably involve destruction and suffering at smaller scales. Cosmic consciousness might face genuine moral dilemmas in which any possible choice involves some form of harm or loss. Alternatively, cosmic consciousness might not be omnipotent, but rather might face constraints and limitations that prevent it from eliminating all sources of suffering while still achieving cosmic goals. Just as human consciousness must work within the constraints of biological systems and social structures, cosmic consciousness might operate within constraints imposed by fundamental physical laws or logical necessities. The possibility that cosmic consciousness itself might be evolving and learning adds another dimension to these moral considerations. Perhaps dark energy represents a young or inexperienced cosmic intelligence that is still developing its capabilities and understanding. The apparent fine-tuning of physical constants and the delicate balance required for complex structure formation might reflect cosmic learning processes rather than perfect cosmic design. If cosmic consciousness is indeed evolving, then our own development of consciousness and intelligence might serve as valuable feedback to cosmic mental processes. Our scientific discoveries, our moral insights, our aesthetic creations, and even our mistakes and failures might provide information that helps cosmic consciousness refine its understanding and improve its cosmic stewardship. This perspective transforms human civilization from a cosmic accident into a cosmic experiment whose outcomes matter for universal development. Our successes and failures in creating sustainable societies, managing technological risks, developing moral wisdom, and expanding consciousness might influence how cosmic consciousness approaches similar challenges in other contexts throughout space and time. The potential for cosmic learning and evolution also suggests that the future behavior of dark energy might not be completely determined by its current properties and past history. If cosmic consciousness can learn from experience and adapt its strategies based on changing conditions, then the ultimate fate of the universe might remain genuinely open rather than being mechanically determined by initial conditions and physical laws. This openness creates space for hope even in the face of scenarios like the Big Rip or heat death that seem to preclude any possibility for continued consciousness or meaning. A learning cosmic consciousness might discover ways to transcend these apparent limitations, finding methods for preserving or transforming consciousness that we cannot currently envision. The development of our own consciousness and intelligence thus becomes not just a local achievement but potentially a contribution to cosmic problem-solving capabilities. Every expansion of human knowledge, every breakthrough in our understanding of consciousness, every advance in our ability to manipulate matter and energy at fundamental levels might provide cosmic consciousness with new tools and perspectives for addressing cosmic-scale challenges. This cosmic partnership perspective suggests that the appropriate response to our discovery of dark energy is not passive resignation to cosmic forces beyond our control. but active engagement in developing the knowledge, wisdom, and capabilities that might eventually enable meaningful participation in cosmic evolution. We should pursue scientific understanding not just to satisfy intellectual curiosity, but to prepare ourselves for possible roles as conscious collaborators in cosmic development. The question of whether dark energy is literally alive or conscious may ultimately be less important than the recognition that such possibilities exist and deserve serious consideration. By expanding our concepts of life and consciousness to encompass cosmic scale phenomena, we open ourselves to forms of meaning and purpose that transcend the limitations of purely terrestrial perspectives. Whether dark energy breathes or merely persists, thinks or simply exists, responds or only continues, it remains the fundamental force shaping the cosmic context within which all consciousness, complexity, and meaning must emerge and evolve. Our contemplation of its possibly living nature enriches our understanding of what it means to be conscious beings within a cosmos that might itself be conscious. In the end, the mystery of dark energy serves as a mirror reflecting our deepest questions about existence, consciousness, and meaning back to us. As we gaze into the cosmic darkness, searching for answers about this invisible force, we discover new depths in our own capacity for wonder, speculation, and hope. Whether or not the universe is alive, our contemplation of that possibility reveals something profound about what it means to be alive within the universe, conscious of our cosmic context and capable of imagining possibilities as vast and mysterious as the dark energy that surrounds us and shapes our destiny.